Hello everyone. In today's video, I'll be talking about Jung's theorem. Let's take a look at the statement of Jung's theorem. So we have been given with x1, x2, xn, which belongs to real space dimension D, such that the distance between any 2 points, the Euclidean metric, is less than equal to 1. So we need to understand, we need to tell that there exists a ball, a closed ball S, such that it covers all these points and it's a minimum one, and the distance between the origin and the boundary, so the radius, it has to have this upper bound. Before we start the proof, let's see the situation when our n will be equal to d plus 1, and let's see when our d is equal to 2. So I think I did not mention about n, so let's just forget about n for a while. Okay. Yeah, so when our d is equal to 2, let's calculate the radius. The radius is going to be 1 upon root 3. It's not very difficult to calculate. Nonetheless, so when we are working in plane, we are trying to say that there exists a circle that covers all the points in the set x1 to xn are all covered within the circle with the radius 1 upon root 3. Let's say that we have n, which is from 1 to d plus, so the maximum limit of n is d plus 1 in this case. And let's say that we have a set S dash, which is a subset of x1, x2, x d plus 1, such that the radius is r of each point, and the convex hull 0 is contained in convex hull. Okay, and we know that the S is the minimum ball that contains all the points. So basically, S dash is going to be, if we try to visualize it on the graph, S dash will be all the points on the circumference with radius r. Okay, this is 0 comma 0. This is S dash. Okay. So I wrote S dash as P1, P2, Pn, such points at the border. So this is P1, P2, P3, and so on. Okay, now let's take scalar multipliers for it. If we have lambda 1, lambda m, we know the property it has to be greater than or equal to 0, uh, such that the sum of the all scalar multipliers should be equal to 1. Uh, Also, it is important to know this property. If you don't know convex hull properly, I'll suggest you to go and watch my previous lecture. So, by the property of convex hull, we get that since convex hull of S dash is 0 is contained in the convex hull of S dash, we can express the convex combination equal to 0. So now let's take a k which is fixed. So I have here from I, okay, I'll just remove this, yeah, and this. Okay. So I have from I equals to 1 to m. Now let's say I have k somewhere between this. Okay, so k is somewhere between m. So if I open this, same thing, it's going to be something like lambda k, it's something like lambda m equals to 1. So if I want to express 1 minus lambda k, it will be something like 1 minus lambda k is equal to sum of all I which are not k till m, of course, of lambda i's, right? So this is what I tried to write here, this step, which is of course going to be greater than or equal to this equation. Now let's try to analyze what this equation is. Okay. Uh, yeah. So let's see. So this is scalar product. We just multiply, open it. Okay. Now the distance of pi. So again, let me remind you all that this was the point pi, right? So, and with the radius r. So this is just r square. This is just r square, and I get 2r square. Okay. So since it's summation, we can take it inside. So we just multiply this with this and this with this. Okay. let's take a look at what is happening here and why it is 0. So this is summation I equals to 1 m pi lambda I, and this is summation of lambda I pk summation I equals to 1 and m till m, whatever that is. But let's just see, sorry. So this is pi, let's say this is pk, this is center, and this is radius. I'm so sorry for my drawing, but it's not very important here. So this is r and this is r. This is the center, okay? Now 0 is contained in the convex hull of this. So the convex combination of this with lambda I is going to be the 0. Again, convex combination of this with lambda k is going to be 0. So let's come back. Okay, so this is 0. So we are just left with 2r squared. So we know that this inequality we can rewrite like this. So 1 minus lambda k from k equals to 1 till m is somewhat greater than equal to this. Now again we put the summation inside. So there are, this is m, this gives me m, this gives me 1 because sum of all lambda k's is 1. We know why. Again, the property of convex hull. Uh, okay, and this gives us this. So let's just rearrange the similar terms. So let's see what we get for r square. We get it less than equal to m minus 1 upon 2m. Now, m was basically for scalar multipliers. So scalar multipliers were from lambda 1, lambda 2 till lambda m. And we have scalar multipliers equivalent to x1, x2, x n, right? So indeed, and our n was d plus 1. So scalar multipliers can be either less than or equal to number of the entities that we have in order to represent it in the convex combination. So by that property, we can substitute, we can I'll just write, we can substitute m as equal to d plus 1. So, okay, if we substitute here, this is what we get. And it's square, we put it in the root, and yeah, we prove what we want. Okay, thank you so much for watching my video, and goodbye.